I'm going to solve some problems on diffraction of light through a single slit. So here's the first question. So here figure shows an interference pattern when laser is shined through a single slit of slit width or size of the hole, 55 micron. The scale is attached to the bottom, so you can measure the distance of the dark fringes. And it also says the distance between the slit and the screen, right, is half a meter. And based on this information, is asking you to find the wavelength of the laser light used in this experiment. So you can also say interference pattern or diffraction pattern, especially when you use a single slit, right? So you can also say a diffraction pattern. So these are the diffraction pattern. As you can see, these bright fringes, right, because of the constructive interference, and these are the dark fringes, right, in between. These are because of the destructive interference. And the main idea is this. So the when you shine any light, right, so light as a wave, and diffraction happens because each point, based on the Huygens principle, each point on the given wavefront works as a secondary source of light, right? And then they interfere actually and produce the diffraction pattern on the screen. This is the screen at some distance. It says L is half a meter, right? Distance, right? And you see this pattern. And intensity plot would be like something like that. So the intensity plot will be something like that. So more than 80% of the intensity will be right here at the central bright, right? And then the intensity changes rapidly. And this is the first dark. This is the second dark, right? And in diffraction, we measure the dark fringes, position of the dark fringes, not the bright fringes, because bright fringes are not symmetrically distributed. So, and here's the formula for measuring the dark fringe position. So, and one more thing, this is called slit width, size of the hole, single slit. So the position of the main position of the dark fringes can be calculated by this formula, right? That's from the theory. So m lambda L over A. So where A is the slit width, right? You can say slit width, the size of the hole. So L is this, and lambda is the wavelength, and Ym is the position of any dark fringe, right? And this formula was derived on the basis of this actually. So the L has to be much bigger than A, which is it, because usually the size of the slit will be really small compared to the this separation. And theta is small. Theta is small angle approximation, right? So any this angle, right? These angles are small, right? These angular separations are small. So then you're given the given pattern, right? You can measure first dark or second dark or third dark, any dark fringes you can measure. So if you want to measure the first, since they are well separated, you can use actually measure first or second dark, doesn't matter. So let's measure the first one, or you can measure second or third, anyone. So this is your y1. This is called y1. It's the distance of the first dark, right, from the center of the pattern. So what would be that? So from the pattern, from the figure, y1, which is the position of the distance of the first dark from the central fringe, is so 6 millimeter, right? 6 millimeter as shown, because there's 5 and 6. This is 6 turns about -3 meter. And then you're given everything, so you're from here, then y1 will be m is equal to 1, right? So lambda L over A, since m is 1, because we have chosen the first dark. If you choose second dark, m is going to be 2, and that's it. So then lambda, which is the wavelength of the light, it will be y1 times A divided by L. So y1 is 6 millimeter, A is 55 micron. Micron means -6. That's given. L is half a meter, right? And then from here you can find that out. Is going to be about 660 times about -9, which is 660 nanometer, because usually the wavelength of the light is expressed in terms of nanometer. So just by measuring this pattern, just by looking this pattern, diffraction pattern, you can easily actually find out, experimentally calculate the wavelength of the given light. And that's what we're going to do actually in experiment. So here's the next question. So you're given this pattern, this interference pattern. That means this is the pattern when you shine light, through a double slit. So this is the double slit top view, right? So these are two slits, two narrow holes separated by this distance d, which is called double slit separation, right? And on the screen you will see these dots, but these small dots are because of the constructive interference, is double slit effect, but you can also see the slow variation in intensity, right? And that's because of the single slit effect. That's called a single slit effect. And this is the intensity plot. Actually, if you plot the intensity plot of this, it will look something like that. And you can clearly see, right, the the intensity, right, the brightness or the intensity of the double slit, right, which is small dots, are actually modeled by the single slit effect, slow variation in the intensity. And that's because of the single slit effect, because this single slit has some finite width, right, and because of that it has single slit effect. So it's the combination of both single slit and double slit actually, right? And it's acting based on this. So you use laser of wavelength 514 nanometers, right? And the screen is placed at 2.25 Hz distance, right? And this d actually slit separation is 800 micron, right? And the slit has a width of 50 micron, right? And based on that, so you're given. So first let's write down all the given variables. So you're given the wavelength of the light used, which is 514 nanometers, -9 meter. And you're given the slit separation. This is small d is slit separation, right, which is 800 micron. Micron means -6. And you're also given the size of the its slit, right, which is called slit size. Size of the slit, right? Is size of the slit size or slit width is also given, is 50 micron, right? That's the given. So based on that, now it's asking, first question is, and one more thing, what is the distance between the slit and the screen? The slit to the screen distance is 2.25. And what is that? That means you have a double slit here, right? This is the side top view, actually double slit, and the screen, right? This is the screen, and this is a double slit, right? Having a distance of d, and each slit has a width of a, right? And you shine a laser light or any light, and you see this pattern on the screen. You see this pattern, right? That's what you say. Based on that, this is big L. Let's see. So it's based on the first question is, what is the linear distance from the center of the viewing screen to the third order interference bright fringe, right? So third here, right here. So this is the center, bright, right? 1, 2, 3, right? It's asking this first question. What is Y3? I means due to the interference. So these small dots are because of the interference, right? And the slow variation is because of the diffraction, single slit effect. So it's asking, what would be the distance from distance of the what's the distance between the third bright fringe, which is this, right, from the center bright, and then you can just use the double slit uh, formula. So double, if you go back and check double slit fringe, right, position, and you will see ym is m lambda L over d. So we're finding the third, right? M3 means third bright fringe. So M is going to be 3, and then Y3 interference, due to interference, is 3 lambda L over D. That's it. So 3 lambda is 514 nanometer, L is 2.25, and divided by D is the slit separation, which is this, is also given, so it's 800 micron. That's it. So that's that's the separation of the third bright fringe from the central fringe, right? And it's going to be, if you do that, 4.33 in millimeter. You can just keep it in meter, or that's fine. That's the first question. Second question is now, what is the linear distance from the center of the viewing screen, right, to the first diffraction minimum? So this is the first dark, right? First diffraction, right, minima. That's the first dark due to single slit. And then single slit we have just used. For single slit, the position of the dark fringes is ym is m lambda L over A. You have to use A, right, because it has to do with the single slit width. And then since it's acting the first dark fringe, so y1 is going to be m is equal to 1, right? And then that's it. So y1 is lambda is 514 nanometers, L is 2.25, and A is the slit size, which is 50 micron. And that's because of this is because of the diffraction, so we put the labeling as y1d. So first dark will be this dark, right, from the center of the envelope, center bright fringe will be at that much distance. So if you do this calculation, so it's going to be 23.1 millimeter. So that's your answer. Okay. So one more question, part C is asking, what happens to the Y3I, right? What happens to the position of the third bright fringe due to interference if the slit spacing increases with no change in slit width? So if you now use a different double slit having increased, having a larger slit spacing, right? Slit separation, what happened to the position of third bright fringes, right? So then we use formula. So because ym, which is the position of the bright fringes in double slit, right, due to interference, is m lambda L over d. So you're using now, you can clearly see, so these are all constant, right? So it's inversely proportional to the d, right? So if you use, now since it says you use a double slit with increased slit separation, then ym has to decrease. Okay, so right, this will decrease. Here's the next question on single slit diffraction. So it says, in a single slit diffraction pattern, what is the intensity at a point where the total phase difference between the wavelets, right, from the top and bottom of the slit is 66 radian? So what is acting is, you have a single slit, right, single hole, and you shine light. These are the wavefronts, and so at some distance, right, L, but it's much greater than the slit width, right? Then this is the middle of the slit, this is the top of the slit, right, and this is the bottom of the slit. So it's acting, what is the intensity at a point where the total phase shift? So it's acting, so these two, so let's say this is a point P, right, where the two light waves, right, from the top and bottom of the slit meet here at a phase shift of 66 radian, right? So it's just acting, the two light wavelets, right, emitted by this individual source on the given slit from the top and bottom at given point P meet with a phase difference of 66 radians. So it's actually what is the intensity of light here, right here, right? It could be completely dark, it could be completely bright, or it could be in between, right? So, and what's the formula? So we have the formula, right? Check out the formula from the lecture. I is given by I naught sine beta over 2 divided by beta over 2 and then whole square. So what is this beta? Beta is the phase angle, is the um, phase shift between two light, I should say wavelets, right, because these are the tiny wavelets from the top and bottom of the single slit, right? And basically this is beta, you're already given actually. This phase shift between these two is already given, is 66 radians. So then you can, so first part is really easy actually. You can just directly use this formula, right, and find out the intensity. So I is I naught. I naught is the intensity at, you know, intensity at the central bright. Central will have, say, intensity I naught, then we're comparing with this intensity. So sine of this is 33 radians, right, divided by 33. Make sure your calculator is in radians when you do this calculation, because this is given in radians, right? So that's it. So the intensity of the light there, right, at given point is that much compared to the intensity at the central bright fringe. And it's almost dark, right, because it's really small, right, it's almost dark. That's the first part. Second part now is action. If this point is 70 degrees away from the central mag, how many wavelengths wide is the slit? Now it's action um, uh, is how many wavelengths, right, wide is the slit. So it's action now this given point, right, that we have just find out, right, is at 70 degrees. This the point whose phase difference, right, the two waves reaching from here and here will have a phase shift of here a phase shift of 66 radians, right, at 7 degrees from the central line, right. So it's actually now based on this information is actually what is the slit width, size of the slit, a single slit, right, in terms of lambda, in terms of the wavelength. So then you can do this. So the phase shift, right, or phi, right, is 2 pi divided by lambda times the path difference, right. This is delta L is the path difference, right, between path difference between these two waves arriving here from the top and bottom of the slit, and that from here this piece is actually a sine theta, right. We know from double slit, right, it's just similar to double slit. If you do the trigonometry, this is the path. Since this L is much greater than A, now these two can arrive here as parallel, almost parallel, and then you draw the perpendicular line, and this extra piece is the represents the path difference between these two waves, which is A sine theta. So just put A sine theta. So this is beta, which is the phase shift, which is given 66 radian, and then this is just A sine theta. That's it. And this beta is given already, right, 66 radians, and 2 pi over lambda, and A sine of 7 degree, right, and then A is going to be 66 lambda divided by 2 pi sine of 7 degree. And if you do that, it's going to be about 86 lambda. So the size of the slit, right, single slit, is about 86 times the wavelength of the light used here. So here's the next question, and this is the experiment, we're going to use the same technique in measuring the hair width, size of the human hair, using diffraction pattern. So this is the diffraction pattern you will see, right? You can see this is the central bright, and then first dark, right? First dark, second dark, third dark, something like that. And this is the pattern you get when you shine a laser light, right? This is the sample holder, and you stick a human hair, thin human hair, right? And then you shine a laser light through it, right? And on the screen you will see this pattern. So it's pretty similar to is single slit diffraction pattern. This is the first dark, right, on both sides, and this width we call let's say W, right? Just by measuring this, you can find out the human hair diameter. So it says it's the first dark to first dark, which we call width of the central fringe, right, is 16 millimeter, right? And this is just the so YM is the position of the dark fringes, right, in single slit is M lambda L over A, and this is W is this is because this is the first dark from one side to the first dark on the other side, so 2Y1, right? So Y1 from this is lambda L over A, so 2 times Y1, which is W, is 2 times lambda L over A. That's it. And then you're solving the size of the hair, right? This is the size of the hair, which is equivalent to the single slit width, is going to be 2 lambda L over W, right? So then, then everything is given. So A is 2 lambda. The laser used in this experiment, it says 640 nanometer. The distance from the slit to the screen is 1 meter, divided by the width is given 16 millimeter, -3. So that's gonna calculate. So if you do this calculation, so the size will be about 80 micron in micrometer. Here's one more problem on single slit diffraction intensity calculation. So it says laser light is shined through a single slit of slit width, A is 30 times the wavelength. The distance between the slit and through the screen is half a meter. And the first question is, what would be the intensity in terms of I naught at a distance 10 millimeter from the central maximum? So first question is, so you use a single slit, right? And this is the central line, right? And this is the slit width, right? A, size of the hole. And it's acting at 10, so let's say this is the point P at 10 millimeter distance from the center, right? What would be the intensity, right? L is half a meter, and A is 30 times the lambda used. So first, to find the intensity, right, using the first you need to find the angular separation. What angle is this point from the central line? So, and you can easily calculate that because theta is then inverse tan. So, but everything has to be in same unit. It will be very small angle, of course, right? So theta will be is 1.45 degree, right? So once you find that, once you find this angle, then you can find out then the intensity formula. What is intensity? Is intensity at given angle theta is in terms of theta is I naught sine beta over 2 divided by beta over 2 whole square. So but what is beta? Where beta is the phase shift, right? Phase difference between the two lights coming from the top of the slit and the bottom of the slit. Yeah. And you can calculate that in terms of path difference, right? This path difference is A sine theta, right? And beta is 2 pi over lambda times A sine theta, because this is just the path difference between these two that was arriving there. So that's it. First find the beta, 2 pi over lambda, right? A is 30 lambda, right? Sine of, and this particular point is at 1.45 degree. Lambda will cancel out. First find that, right? So first you have to find the beta, right? and this will be in radians though. So 2 pi into sine 1.5 degree, very small angle, times 30. So it's going to be 4.93, right? And then that's it. That's all you need to know. Then your intensity of the light at point P is I naught sine 4.93 divided by 2, 4.93 divided by 2, and then whole square. But make sure your calculator is in radians, right? And then calculate that. So it's going to be 0.25 I naught, where I naught is the intensity of the central maximum, right? Okay, so that's the first part. So the second part of the same problem is, what is the phase difference between the two waves from the top and bottom of the slit, right? So it's basically asking from the same diagram. It's just asking what is the phase shift or phase difference between the two wavelets, right? Emitted from the top of the slit and bottom of the slit, right? Phase shift. So basically it's asking the beta, right? We have already calculated actually. So 2 pi over lambda times the path difference between these two, which is a sine theta. Basically we have already calculated that, right? So 4 so just follow this, 4.93 radians. Okay. So the next question is 4. This is 4.76. 4.76. So I have used the same here. 4.7376. Okay. Now next question is asking what is the phase difference between the two waves from the top and the middle of the point of the slit. So that means this, right? It's asking what is the phase. The point P is same, right? It's asking from the top of the, what is the phase difference between the two waves arriving from the top of the slit and from the middle of the slit. And that's then the phase, the path difference between this and this will be, right, half of a over 2, because this is a, right? Because this will be a over 2, half the slit width, sine theta, that's it. So then do the same thing. Beta is 2 pi over lambda, a over 2 sine of theta, right? Because 2 pi over lambda path difference, and path difference is this, and 2 pi over lambda, a is 30 lambda, right, divided by 2, and sine of 1.45 degree. So it has to be, right, the half of that, right? So 2.38, and this is also in radians, right? So half of that. Now I'm going to solve some problems on example problems on polarization of light. So here's some examples. So in general, actually, the light from the bulb, sun, is usually unpolarized. That means it has electric field oscillations in many random directions. But you can have a polarizer, right? And polarizer, and then it will allow only the oscillations parallel to its axis, optical axis, right? And it will only allow this, oscillation, in y direction in this particular. So this is called then said to be have a polarized light. This is unpolarized light. This is polarized light, right? And if it is unpolarized light, so if the original intensity is I naught, right, then the intensity after passing through the polarizer is going to be half almost half of the original intensity. Why? Because it has any random polarization, and all this polarization can be decomposed into vertical, right, and horizontal polarization, right, components, and all the horizontal components will be cancelled out, right. And on average, actually, the vertical components and all the horizontal components are almost equal on average. And but since it cancel out all the horizontal oscillations, it will only allow the vertical oscillations. The intensity will be almost half the original intensity. So that's the main idea. So here's some problem on polarization of light. So it says natural light passes through a perfect polarizer. What fraction of light passes through? Now a second polarizer is introduced with its axis inclined at an angle of 22 degree relative to the first. What fraction of the light incident on the second polarizer pass through? What fraction of light entering the first polarizer emerges from the second? So here's the first question. So you have a polarizer, right? That says axis of polarization is vertical, right? It will allow only lights parallel to its optical axis, right? So you have unpolarized light. That means it has a polarization in any random direction. This is the unpolarized light, and when it passes through the first one, right? What would be the so if the original intensity is I naught, this is the first polarization, right? Polarizer. So the light passing, the intensity of the light after passing through the first polarizer will be what? Half of the original intensity, because on average all the horizontal oscillations will be blocked. It will allow only vertical oscillations, so it will be half of the original intensity, 50% of light. Now it says you put uh, you know a second polarizer, right? You put a second polarizer whose axis is uh, 22 degree relative to the first, right? So your theta is 22 degree with the vertical. Okay. So then what's the intensity then, right? So the new intensity from the Malus law, right, is the original intensity. Now this works as the original intensity for the second polarizer, and I naught, right, and then cos square of the angle. Angle is 22 degree relatively, right, and that's the intensity passing through the second polarizer. Let's say I2. Then 0.86 divided by 2, right, times I naught. That's what we get, right? So then relative to, so here, so it's going to be 86% will pass through, right, to the second polarizer relative to the first polarizer, right? But if you now calculate, this is going to be 43%, right? I naught will pass through the second one relative to the original intensity. Okay, so relative to the first one, it will allow 86%, right? Because 86 divided by 2, because it has already gone half. But relative to the original, it will be only 43% here after passing through the second one. Right. Okay, here's the next one. So next question is, I start with two ideal polarizers, right, with their polarization axis at right angles to each other. Obviously, no light will get through. Now now insert a third ideal polarizer with its polarization angle at an angle 45 degree with relative to the others, right? what fraction of the natural light pass through the will pass through the set of three polarizers. So here's how you can visualize. You use three polarizing sheets, right? Here's the first polarizer, right? And here's the second one, right? But then you put a third one, you put this another one, so that um, its axis is 45 degree relative to the first and second respectively, right? So here's you have, this is the unpolarized light passing through, this is the unpolarized light, right? And so light passing from here is, let's say, I1, light passing through the second one is, let's say, I2, and light passing through here is I3. So first of all, you can immediately say if I0 is the initial intensity, I1 will be I0 over 2, right? And then what would be I2? I2 would be uh, original intensity, which is half of I0, right, times the cosine of 45 degree from Malus law, right? And it's going to be 0.25 I0. Now then do the same thing, right? The I3 will be, now since they are 45 degree off from each other's axis, right? Again, it will shift by 45 degree. So, but now for I3, I2 is the original intensity, right? And again 45 degree. But I2 is 0.25 I0 times cos square 45 degree. So the final intensity after passing through the third one finally will be 0.125 I0, which is about only 12.5%. So after using the three, polarizers like that, with the middle one at 45 degree angles off from first and third, right? The total intensity has gone to only 12.5%. So here's another problem on polarization of light, and this is the polarization by reflection, right? And this is about Brewster's law. It's called Brewster's law. When the angle of reflection and angle of refraction becomes 90 degree to each other, this light will be completely polarized. The reflected light will be completely polarized, and it will have a polarization, perpendicular to the plane of the paper, right? It will not have any other components. So that's what the Brewster's law said. So first question: at what angle of incidence will the light reflected from the water, right, will be completely polarized? So this is a water. This is a pool, right? So at what angle, right? Angle of incidence. At what angle of incidence, right, will the light reflected off the surface will be completely polarized, and this is also called Brewster's angle. And you can directly use the formula actually for the first one. Brewster's angle is given by inverse tan n of water divided by n of air, n2 over n1. So second medium is water, and the first medium index of fraction is air. So that's it. So you can this one directly calculate 1.33 divided by 1, and the Brewster's angle is so at about 53 degree angle, right? If you shine a light on polarized light at an angle 53 degree, then the partially reflected light, right? This light will be completely linearly polarized. Okay. So second part is, does this angle depend on the wavelength of light? Yes. Answer is yes. Why? Because n index of refraction depends on depends on lambda. That's right. Because blue light, right? Blue light has the index of refraction for blue color is slightly higher than index of refraction for the red color, because they have these colors have different energies, right? That's why yes, the angle, this Brewster's angle depends on what color of light you shine.